All right. Hey guys. We'll be reviewing a little bit about lecture 31, which is calorimetry. Just give me 1 second over here. All right. And we're just gonna go over calorimetry and some of the reasons why we use calorimetry and the types of it. Hopefully by now we all have a little bit of idea of what calorimetry is and calorimetry is and why it is important for us to know how to use it. And just as we've been studying in the laws of thermodynamics, we are normally trying to measure the quantities of energy that would go either in or out of our reactions. And if we think a little bit about it, we don't really know um, how do we trap that energy and measure it, or what are the ways that we use it? Do we just grab our substances or our samples of energy and just put it inside of a box and just try to find a way to measure it? And so to be able to measure those changes in energy, then we normally use calorimetry. That's why calorimetry is for. Um, and just as we said, calorimetry is just the process that we use to measure those changes of heat that are either released or absorbed during our chemical reactions. And there are a lot of reasons behind why do we need calorimetry, or why calorimetry is important for us. And one of those is that when we know the change of heat, whether or not we can know whether or not a reaction is endothermic, which means is absorbing heat, or exothermic, which means is releasing heat. Calorimetry can help us with those things because we can easily measure the changes. We can easily measure how much heat do we have in the beginning and how much heat do we have at the end. And this machine over here is a calorimeter. Sorry. And at first it looks kind of scary, and it looks that it's really complicated and really expensive actually. But the truth is that we can make a calorimetry out of really easy and simple things. And so how do we do it? We basically need to do three things. The first is we need to take a substance that we know well. And normally for those reactions, we would want to use water. Why? Because we know we know how water responds to heat. And if we just grab a thermometer and we put it inside of the water, we can easily measure its boiling point. And we really know a lot about water, and it's really easy for us to use it. And then the second thing that we need is we need to run a reaction that will let go in or out heat. Sorry, I forgot a bit. They will let go heat in or out into the water. And we do that so that we can measure the water's change in temperature. And when we do that, then this allows us to know exactly how how much heat it went into the water. Because just as we were saying in the beginning, we measured the water and the temperature in the beginning, and then after our reaction, we can measure the final temperature, and we know how much it changed. And from this, we can conclude that the heat came from the reaction, and we also know how much heat comes out of the reaction as well. So that basically means that our heat that got into the water, it's equal to the heat that came from our reaction. So those two things are basically the same. And in calorimetry, we have two different types of measuring calorimetry. We have constant pressure and we have a constant volume. And we're gonna go over the easy one first, which is the constant pressure, and it is also known as the coffee cup. And this is really a very simple way in which we can create a calorimeter and we can use it in our, really we could even make it in our houses. We would really just need a couple of things that we can find at home. The only thing that we would need would be two normal styrofoam cups, like the ones that we can see over here. And we need to stick them together. We will have to put them together so that this can isolate the reaction from the outside, from the surroundings. And so what this coffee cup calorimetry is basically, we have those two cups and we put water inside of one of our cups. And we can also put our reactant, we can put any of our reactants, and this will be floating inside of the water. We would of course know the amount of water do we have and its temperature already. We would have to put our material in grams inside of it, and we would have to have a thermometer and stir, basically something that can help us to mix our solutions. And this temperature will change, and it will be really easy to measure the start and the finish temperature. Coffee cup calorimetry calorimeter is really a great type for measuring just heat flow in chemical reaction, and it really doesn't need any sophisticated equipment. We could even do it with two cups, a lid, a thermometer, and something to stir the solution. And just to kind of understand a little bit more, when a chemical reaction occurs here inside of the coffee cup calorimeter, the water is what absorbs the heat of the reaction. And since these two styrofoam cups insulates the reaction from the outside surroundings, then we can obviously assume that all the reaction's energy is absorbed into the water. And the change in the water temperature is used to calculate the amount of heat that has been absorbed or either are absorbed or released in the reaction. So the temperature of our water will tell us how much heat of our reaction was released or absorbed. And so the coffee cup is really a very simple way in which we can measure calorimetry. The second type of calorimetry is, just one more thing, is that our heat of our, using coffee cup calorimetry, we can say that the heat of our substance, which is, we said it's equal to the heat that was absorbed from our water. And another type of calorimetry, it's bomb calorimeter, which is a constant volume. And the reason why we call it a bomb calorimeter, it's because we're actually burning or blowing up out stuff that are inside of a container. And for this bomb calorimeter, we normally use it to measure combustion reactions. And just as we were saying, the reason why we call it bomb is because we just need a stainless steel container, which is here recognized as a bomb cell. and we would have to have a sample or something that is flammable because we'll burn it. And so we'll have to put it inside of our bomb cell or of our stainless steel cells, and we're also add a lot of oxygen into it. And we'll have to seal it really tight because this will be inside of a bigger container, which will have water and other different tools that we'll be using. We'll also, just as we said, we'll burn the sample that we have inside of the bomb cell. And we'll also have to have our temperature thermometer. We'll have to have some wires and a stirrer to mix the water so that the heat can be dispersed. And when we burn this sample inside of the bomb cell, this creates the temperature in the bomb container or the bomb cell to raise. And when this bomb container's temperature raises, the big container that has water, which is over here, its temperature also raises because of the heat that it's been producing from our bomb cell. And we now have a temperature that we can change into amount of heat. And in this case, our heat of our reaction, or heat produced by our reaction, then would be equal to the heat gained by our calorimeter. And of course, there are a lot of different things that could change the actual temperature, change of temperature, for example, the thermometer or the stir or any of the other things, even the bomb cell, its weight and everything. And instead of trying to figure out all the heat of all the components of the calorimeter, every single one of those things, we just need to calculate one heat capacity, or probably just the whole system. And we can get that by just running a reaction that gives off a known amount of heat. And then we check that amount of heat. We check if that amount of heat gives us some amount, and our calorimeter changes by some temperature. Then we know that the overall heat capacity of our calorimeter is just this equation that we have right here, which our heat reaction would be equal to the calorimeter, sorry, times our delta, or our change in temperature. And we can honestly rearrange this equation to calculate anything that we need. If we need the difference in temperature or our calorimeter. So we're just gonna go over a few examples of how we can use this equation. Obviously in further lectures, we'll be able to use different variants of this equation as well to be able to calculate different things. But just basically to review a little bit, we have two types of calorimeters, which is coffee cup calorimeter and the bomb calorimeter. And bomb calorimeter would probably be the best option that we have. It's probably a little bit more expensive and it requires a lot more of effort, but it certainly gives us a little bit more certain measurement of the changes in temperature, which is something that we really want to have. And so we're just going to review a couple of examples on how to use our equation to calculate the changes in temperature and the heat of our reaction. And so in this example, it says, what would be our C calorimeter if we burn 2.0 grams of sulfuric acid, which increases the temperature of the calorimeter by 6.35 Celsius degrees? And just so we know, the combustion of sulfuric acid releases 10.35 kilojoules over grams. And so the way that we use this equation is we'll have to rearrange our equation because we're now solving for our C calorimeter. And so solving for our C calorimeter, it would be equal to a negative heat of reaction divided by our delta, or change in temperature. And so we just plug out all of our data, which we know that the heat of our reaction of our sulfuric acid is minus 10.35 because it's releasing, this combustion is releasing heat. And so we plug that here and we multiply that by the 2 grams of sulfuric acid that it's going to burn. And then we divide this whole equation into our change of our temperature, or delta temperature, which is 6.35 Celsius. And we solve for this equation and we know that 3.259 kilojoules over Celsius is how much our calorimeter is burning. In this equation. And just to have a little bit more of details about calorimetry, we also have our delta H of reaction and calorimetry, which is the heat that is either consumed or absorbed during a chemical reaction. And some of them would be exothermic, which means that they give off energy, or some of them will be endothermic, which means that they gain energy. And so for this problem, it says 1 mole of propane is combusted with excess oxygen in a constant pressure calorimeter with a heat capacity of 9.735 kilojoules over degrees Celsius. The temperature of the calorimeter changed by 139 degrees Celsius. What is the change of enthalpy per mole? So we have to make sure of every single part of our question, or what are we being asked for the combustion of propane. So we're asked, what's the change of enthalpy per mole for the combustion of propane? And so we know that our heat of reaction, it's equal to our heat that is absorbed in our calorimeter. And we can also say that our heat of reaction would be equal to our delta H reaction. So anything that we combust would be equal to the heat of our calorimeter. And we will change that for our delta H of reaction, or our change on enthalpy. So delta H of reaction can also be recognized as our change on enthalpy. And so any time that we're trying to solve for the change of enthalpy, we have to make sure that we are doing it for 1 mole of any of the substances that we're using, because that's one of the rules that we have to be able to use our delta H of reaction. And so we'll just use this equation when our delta H of reaction will be equal to our C calorimeter times our delta T. And because we are combusting this energy, we'll have to switch our negative sign, and we'll have to move it around here, and then we'll just plug our numbers. So for our C calorimeter, we have minus 9.735 kilojoules over degrees Celsius times our temperature, which is 139 degrees Celsius. And when we solve for this, then we have minus 1353 times 6 kilojoules. And something to remember is that every time we have a negative sign, this means that our system gave up energy. This means that our system gave up 1353.6 kilojoules of energy. And anytime that we have this, then we can say that we have an exothermic process because we gave up energy. And so just another example real quick. There are basically the same really simple examples. We have 1 mole of ethane is combust with excess oxygen and a constant pressure calorimeter with a heat capacity of 6.98 kilojoules times degrees Celsius. The temperature of a calorimeter changed by 116 degrees Celsius. What is the change of enthalpy per mole for the combustion of propane? So we're being asked the same change of enthalpy. Make sure we have 1 mole, so we can continue with our equation. And we do the same. We solve for our delta H of a reaction, and we just plug in our numbers. We have negative 698 kilojoules over degrees Celsius times 116 degrees Celsius, which gives us minus 809.68 kilojoules. And we know that this is a exothermic process. We know that this is giving up energy because of our negative sign and our reaction. And so this was just a little bit of review about calorimetry. Hopefully this is something that can help you guys to just practice a little bit more, and we'll continue to learn more things in further lectures that will help us better understand how can we use those equations to solve for calorimetry and enthalpy as well.